we now have all the building blocks we need to build a modern neural network. We have the basic neuron, which is doing a simple linear calculation. We have those nonlinearities, whether that's the sigmoid or the binary or the rectified linear unit. And then we know how to pack together a bunch of neurons together to get more and more computational power. This is a rendering of a typical neural network that you'll see in the literature. You got a bunch of inputs here. You have a bunch of neurons in blue, and we have multiple layers. Here I've just done one hidden layer, but of course there can be more of these. And then we have our various outputs here, one or more. And of course what we're doing here is we're going to learn the weights associated with all of these connections. And now you can start to see why this is going to get complicated. In this particular network that I've rendered here, I have what's called a fully connected neural network. Every input here in white is connected to each of the hidden layers, and each of the hidden layers themselves is connected to each of the output layers. Associated with every one of these links is a weight for our linear model. What's happening inside the hidden unit is, well, we don't know. Some linear, some nonlinearity, that's a choice we have to make. So how many layers? How many neurons? What is the connectivity of it? Those are the design decisions that go into the networks. Now here's the remarkable thing about a network is not just that empirically it seems to work, but we can say something theoretically about it from the universal approximation theorem, which says a network with a linear output layer, so there's no nonlinearity here, and one or more hidden layers with having the rectified linear unit nonlinearity or a sigmoidal nonlinearity or any type of what's called compressive activation function can approximate any continuous function. That's really remarkable. That's really remarkable that these calculations, with nothing more than a bunch of linear models with some pointwise nonlinearities tacked on here, can approximate any continuous function. But here's the rub. Training this network may be very, very difficult. So it's one thing to say that this network can do something. It's another thing to say, how does it do it? How do you learn all of these weights? Not just 3 weights associated with 3 unknowns, but now a significantly larger number. And a big part of the neural network literature inside and outside of computer vision is essentially trying to figure out how to train these networks in a way that is efficient and stable and consistent. And we're not going to get into that in this class. This is not a neural network class, this is not an optimization class, and it's certainly not a machine learning class. But we are going to talk a little bit about how to train these neural networks, because I want you to understand that at its core is nothing really significantly different than what we have already seen throughout this course. What is different are all the bells and whistles that you have to add on to it to get this thing to work in practice, for which you will want to take a machine learning or a more advanced computer vision class that gets into that. But what we're going to see next is what is the underlying mechanism for training, not just with the simple delta rule that we saw earlier with a single neuron, but what happens when you have these multiple hidden layers and these multiple neurons and the nonlinearity. How do we do that training? And I'll give you the scaffolding to understand that. And from that, the rest is to be learned in a different class.